Hi, today we'll be discussing MPI and Python in the deep learning realm. My name is Kawthar Shafie Khorassani and my co-presenter is Arpan Jain. We're both PhD students at The Ohio State University working in the network-based computing laboratory. So our presentation today will go as follows. I'll first describe what MPI is and why it's important with some examples, and then Arpan will delve into its relevance in the field of deep learning. So first off, what is MPI? MPI stands for the Message Passing Interface. It's a message passing standard and provides a protocol for communication, which is used in parallel computing architectures. It provides a means to exchange data amongst multiple processes in a parallel program. Now, MPI is crucial in high-performance computing and in the deep learning realm in order to scale a program and parallelize it across multiple machines. The different types of communication with MPI that we'll delve into in this presentation are point-to-point communication and collective communication. In order to utilize MPI in your program that is done in Python, there is an MPI for Python package called MPI for PY, which can be found over here. The first form of MPI communication is referred to as point-to-point communication. And as the name suggests, this is a form of communication between 2 points, a sender side and a receiver side. So in MPI semantics, we would refer to these as MPI send and MPI receive. The idea is that you would have two processes attempting to communicate data to each other. So for example, process A is attempting to send data to process B. In this case, process A would be considered the sender process, while process B would be the receiving process. The semantics would define the data, the count of the data being received, the destination it would be sent to, and so forth. So providing some sort of unique identifier that would match process A's sender data to process B's receiving location. Now for a specific example of MPI send and receive in Python, you would first have to define some basic MPI semantics for your program and also import MPI for PY if you're doing this in Python. Now think of this program as being run parallelly. So process 0 would execute this portion of code and process 1 would execute this portion. Process 0 over here is the sender process. So at process 0, we would define the data, and then we would say that process 0 is sending this data to destination process 1. And we would also define a unique tag 11 over here. Process 1 would say that our data is equal to whatever data is received from the source, which is process 0, that has this unique tag 11. We use these tags in order to match the correct receiving process location with the sender process that's being sent. Now for a more visual example, process 0 has this data already stored and it's trying to send it to the receiver process, process 1. Once that data is sent, process 1 now has that data. Now MPI collective communication. So different than point-to-point communication, MPI collective communication includes more processes. So there's one-to-all communication where one process is communicating to many processes, and then there is many-to-all communication where many processes are communicating with each other. The input would be the data from the multiple processes over here or the data from the one process in one-to-all. And the output would be some sort of reduced or modified data that's stored at each of the processes involved. There are different collective operations shown here. We're going to delve into MPI All Reduce, MPI Broadcast, and MPI Reduce. So MPI Broadcast is a form of communication where a root process is defined and that process sends data to all the other processes involved. So in this example, we have this data object and we're saying that the root is process 0. So process 0 will be sending this data to all the other processes involved. Again, define your semantics. Now, if the process 0 is running this piece of code, that process now has this data stored. If it's any of the other processes, they don't have any data currently. And all of the processes will be executing this line of code. So if the process is 0, it'll say that it will be sending the data to all the other processes. And if it's any other processes executing this line of code, it will be waiting on the data to be sent from process 0 to its process. So a more visual example is process 0 holds this data value. Once it's broadcast, now all the processes hold this data value. Another example is MPI Reduce. The difference here is that you'll have a data object, a reduction operation, and a root process that you would store the value at. So this reduction operation is applied to all the processes, and then the reduced value is then stored at the root process, which is process 0. These are some more examples of reduction operations that can be applied. And to visualize this in an example, processes 1 through 4 and process 0 each have a data value. A reduction operation is then applied, and then the new value is then stored at process 0. So the sum of these is 32. The next example is MPI All Reduce. MPI All Reduce is different from Reduce in that all the processes are communicating with each other, so there's no root process defined here. So to visualize that, you have process 0, 1, 2, and 3 still holding these values. They apply a reduction operation on them, but now this reduced value of 22 is then sent back to all these processes. So this is the reduced value that's stored. So this slide shows an overview of the MPI H2 project, which is an MPI library that is developed at The Ohio State University for the past 19 years. It's empowering many top 500 supercomputers. In order to use this MPI library with your project, you can reach out to us and we can help you get that set up. Now, Arpan will delve into the relevance of MPI in the field of deep learning.
Now we know the MPI, let's talk about its application. Before moving to deep learning, I will briefly explain the machine learning. Machine learning is a set of algorithms that are used to predict the output based on an input. In this case, the input is the image of a car, and output is whether there is a car in the image or not. In machine learning, we have to calculate the features. In other words, the distinct properties of the input that can be used to make the prediction. However, in deep learning, we don't have to do this. Deep learning automatically calculates these features. Therefore, deep learning is a set of machine learning based on neural networks. So, how do we train these deep learning models? We show bunch of images to deep learning model and compare the prediction with actual output to calculate the gradients, and these gradients are used to calculate or update the model. We can't pass all the images we have in one shot because of memory limitation and some other theoretical issues. Therefore, we pass a set of images. In this example, we are passing 10 images at once, and we have 100 images. It will take 10 steps to go over all the images. But this approach is not feasible when we have million images or 100 million images. So, and we can't train the model on such a big data set. So can we use the multiple machines to speed up the training of deep learning model? So basically, in this case, we have divided our 100 images into 5 set of 20 images each and gave them to 5 different machines. By doing this, we are able to decrease the training time by a factor of 5. But there is a big problem here. In this case, we are training model on 5 different set of images with no synchronization. Therefore, in the end, we will end up with 5 different models but we want to train a single model. So, how can we do it? We can use AI to synchronize the model. So basically, after calculating the gradients on each machine, we can use or reduce function to calculate the average gradients and use them to update the model. In this case, we are using the we are calculating the element-wise sum and then we divide it by the number of machines to calculate the average uh, of the gradients. In this way, we are synchronizing the training and will have a single model at the end. And we are so in this talk, we talked about MPI and how can we use it in Python using MPI for py library. Then we used MPI to accelerate the training of deep learning models. So with this, I conclude the talk. Thank you everyone. Feel free to contact us via mail for any query. Thank you.